Hi everyone, welcome back to the last section, Creating Machine Learning Architecture. In this section we will be defining a complete machine learning architecture that is able to pre-process the input data. We're also going to show how scikit-learn manages complex pipelines and how it's possible to fit them and search for the optimal parameters in the global context of a complete architecture. Now we move on to the first video of this section, Machine Learning Architecture. In this video we're going to learn about some common steps which are normally included in almost any ML pipeline. Until now we've discussed single methods that could be employed to solve specific problems. However, in real contexts, it's very unlikely to have well-defined datasets that can be immediately fed into a standard classifier or clustering algorithm. A machine learning engineer often has to design a full architecture that a non-expert could consider like a black box where the raw data enters and the outcomes are automatically produced. All the steps necessary to achieve the final goal must be correctly organized and seamlessly joined together in a processing chain similar to a computational graph. Unfortunately, this is a non-standard process, as every real-life problem has its own peculiarities. However, there are some common steps which are normally included in almost any ML pipeline. This is the schematic representation of this process. The first step is data collection. It is always the most generic because it depends on every single context. However, before working with any data, it's necessary to collect it from all the sources where it's stored. The ideal situation is to have a comma-separated values (CSV) dump that can be immediately loaded, but more often the engineer has to look for all the database tables, define the right SQL query to collect all the pieces of information and manage data type conversion and encoding. It's important not to underevaluate this stage because it can be much more difficult than expected. I suggest, whenever possible, to extract flattened tables where all the fields are placed on the same row, because it's easier to manipulate a large amount of data using a DBMS or a big data tool, but it can be very time and memory consuming if it's done on a normal PC directly with Python tools. Moreover, it's important to use a standard character encoding for all text fields. The most common choice is UTF-8, but it's also possible to find DB tables encoded with other char sets, and normally it's a good practice to convert all the documents before starting with the other operations. A very famous and powerful Python library for data manipulation is Pandas, which is part of SciPy. It's based on the concept of data frame and implements many methods that allow the selection, joining, grouping, and statistical processing of datasets that can fit in memory. A common problem that must be managed during this phase is inputting the missing features. Next step is normalization. Normalizing a numeric dataset is one of the most important steps, particularly when different features have different scales. Very often it's enough to use a standard scaler to whiten the data, but sometimes it's better to consider the impact of noisy features on the global trend. Use a robust scaler to filter them out without the risk of conditioning the remaining features. The user can easily verify the different performances of the same classifier when working on normalized and unnormalized datasets. As we're going to see in the next step, it's possible to include the normalization steps in the processing pipeline as one of the first actions, and include the C parameter in grid search in order to impose an L1-L2 weight normalization during the training phase. The next step is dimensionality reduction. This step is not always mandatory, but in many cases it can be a good solution to memory leaks or long computational times. When the dataset has many features, the probability of some hidden correlation is relatively high. Testing the impact of each factor during the initial phases of the project can save time that can be useful when it's necessary to evaluate slower and more complex algorithms. The next stage is data augmentation. Sometimes the original dataset has only a few non-linear features, and it's quite difficult for a standard classifier to capture the dynamics. Moreover, forcing an algorithm on a complex dataset can result in overfitting the model because all the capacity is exhausted in trying to minimize the error, considering only the training set, and without taking into account the generalization ability. For this reason, it is sometimes useful to enrich the dataset with derived features that are obtained through functions of the existing ones. Polynomial features is an example of data augmentation that can really improve the performance of standard algorithms and avoid overfitting. In other cases, it can be useful to introduce trigonometric functions. The former allows a simpler management of radial datasets, while the latter can provide the classifier with information about the cross-correlation between two features. In general, data augmentation can be employed before trying a more complex algorithm. For example, a logistic regression, that is a linear method, can be successfully applied to augmented nonlinear datasets. The choice to employ a more complex model or to try to augment a dataset is up to the engineer and must be considered carefully, taking into account both the pros and the cons. It's preferable not to modify the original dataset, but to create a scikit-learn interface to augment the data in real time. In other cases, a neural model can provide faster and more accurate results without the need for data augmentation. Together with parameter selection, this is more of an art than a real science, and the experiments are the only way to gather useful knowledge. Then comes data conversion. This step is probably the simplest and at the same time the most important when handling categorical data. A general rule concerns the usage of integer or binary values. The latter is probably the best choice when the output of the classifier is the value itself, because it's much more robust to noise and prediction errors. On the other hand, one-hot encoding is quite memory-consuming. Therefore, whenever it's necessary to work with probability distributions, like in NLP, an integer label can be much more efficient. Post that comes modeling, grid search, and cross-validation. Modeling implies the choice of the classification or clustering algorithm that best suits every specific task. We've discussed different methods, and the user should be able to understand when a set of algorithms is a reasonable candidate and when it's better to look for another strategy. However, the success of a machine learning technique often depends on the right choice of each parameter involved in the model as well. As already discussed, when talking about data augmentation, it's very difficult to find a precise method to determine the optimal values to assign, and the best approach is always based on a grid search. Scikit-learn provides a very flexible mechanism to investigate the performance of a model with different parameter combinations, together with cross-validation, that allows a robust validation without reducing the number of training samples. And this is indeed a more reasonable approach, even for expert engineers. Visualization. Sometimes it's useful or necessary to visualize the results of intermediate and final steps. In this course, we've always shown plots and diagrams using matplotlib, which is part of SciPy, and provides a flexible and powerful graphics infrastructure. As this is an evolving sector, many new projects are being developed, offering new and more stylish plotting functions. One of them is Bokeh, which works using some JavaScript code to create interactive graphs that can be embedded into web pages too. That's all about machine learning architecture.